lecture, and then I'm going to say, next week, I'll spend 20 minutes or so reviewing main concepts of bioinformatics. I would like to spend the next hour and 10 minutes going over genetics problems, because that's really, I think, what you guys need is some help going over those problems. And then the following Monday, which is the 18th, I will go over problems from 5 to 6:30. We'll take a break till 6:45 or so, and then I have the room till 8 o'clock. That second part will not be webcast, and then you can continue to ask more questions, okay? So that's how I'm going to try to do that, okay? I also have extra office hours. The office hours get really crowded. Anyway, this is the trace you'll get. Here's the information you get. You'll work through it, and then when you blast it, you're going to get data like this, and you'll work with that to generate a tree that shows relationships, okay? Here's the complementation stuff. Here's on the YPD plate. Why does everything grow? It does not have the ability to make histidine, so why can everything grow? What is special about the YPD plate? It has histidine. And what we'll do is we'll use a replica plating tool and some sterile velvet, and you'll use that to transfer these yeast from this plate onto the SD plate. And when you first transfer them, you don't see this growth. You barely see the tracing of those cells because you transfer a subset of those cells. But with time, if they're able to grow, they go from 1 cell to 2 to 4 to 8. You see a colony, but the colonies merge basically, you see growth like this. So would you say that this mutant here and this mutant complemented? No, because they failed to grow. So are they in the same complementation group or different? Same. Excellent. Okay. Now these did complement. Now what I don't know is if this mutant happens to be in the same complementation group as this mutant or this with this, because I've not done those pairwise matings. Okay. And remember, there's a pathway. Think about chemicals. And remember, we generated diploids, and we did that. Okay. So right now, I'd like you to try to solve this problem. I'd like you to figure out the order of the pathway. What's the pathway in terms of biochemical pathway? What chemicals are made first and last in this pathway, and which mutants are blocked at each step in that pathway. Okay. So I'm going to give you 2 minutes to do this, and then we're going to go over it as a group. And you'll see you really only need about 2 minutes. I hope. You can work together. Okay, it's been 2 minutes. Who got the answer? Anyone get the answer? Raise your hands. Be proud. About 7 people. So let's quick run through this right now, and I'm going to go over the logic with you. I tried to reproduce the data on the board here. I did it quickly, so I hope I didn't make mistakes, but let's just run through the first set of data here. 1 and 2, well, first off, 1 will always fail to complement itself. So 1 and 2, they fail to complement. Are they the same complementation group or different? Same, and they lack the same information. So I see that C accumulates in these. So I know there's a block here. That's mutant 1 and mutant 2, and also mutant 5. And they're rescued by A, B, and D. I don't know the order. All I know is A, B, and D are to the right of it. Anyone not see that? Anyone not see it? Okay, everyone sees it. So let's move on. Did everyone see it? Okay, excellent. So let's do mutants 3. It fails to complement 7. So that tells me these are in the same complementation group. And A accumulates, and B and D rescue it. So from that information, I know that was mutants 3 and 7. And I know B and D are in this direction. So I already know it goes C to A, correct? So let's continue. Anyone not see that? Raise your hand if you don't see it. Okay, looks like everyone sees it. Now let's look at mutant 4. Accumulates E, rescued by A, B, C, and D. So that tells me it must be here with A, B, C, and D to the right. And that was mutant 4. Well, I now know it goes E to C to A to either B then D or D then B, right? I don't know which of those. So let's do the last one, which is mutant 6 here. Whoops, I know this is a mistake. What was this supposed to be? Is it just B? Okay. So mutant 6 is like this with D, and B is to the right, and that's mutant 6. So we now know the path of production is E to C to A to D to B, and we know where each mutant is blocking that pathway. Anyone not see that? Okay. So since you guys know how to do that, I will try to make sure I put one of those on the lab exam. Okay? Question. So the question is, what's the least number of genes? What we've determined is that there was 1 set of information here, there was 1 set of information here, 1 set of information here, 1 set of information here. So based on this, there's 1, 2, 3, 4 steps at least. Okay? Because each complementation group represents a piece of genetic information or a gene. Okay? And yes, a complementation group can consist of only 1 mutant because we only studied 7. If you really do this analysis, you might study 1,000 mutants before you feel confident in your data. Okay? This is only 7. So a complementation group can consist of only 1 mutant. I've had students sometimes say, oh, I didn't put that down on the exam because I thought you couldn't have a group of 1. You can, it's just lonely, okay? All right, Mendelian genetics. You got to understand meiosis. So let's do mitosis, and then we'll do meiosis. With mitosis, 26, so on humans, 46 chromosomes, 23 pairs. I duplicate, so 1 chromosome, double strand, I duplicate. This is still a chromosome. It's composed of cystic chromatids. They share a centromere. This is 1 chromosome. During mitosis, 46 of these would line up. The moment I separate those chromatids, we call this a chromosome, okay? Because it's no longer sharing a centromere, okay? Now, I'm not going to ask you typically how many chromosomes are present in A2 or something like that. I will pick an endpoint where it's clear, because if these are in the same common cytosol, what do you call it, right? So I always try to pick an endpoint. But anyway, do this, separate. Original number of chromosomes on each side. 1 duplication, 1 division. If it was meiosis, remember, I pair up this pair, the second pair can assort, line up independently of that, the third pair, the fourth pair, the fifth pair, etc., right? So Mendel's second law refers to the fact that these chromosome pairs align independently of one another, okay? And Mendel's first law refers to segregation. That means for a given pair in mitosis or meiosis, you're going to get 1 of those chromatids, okay? So, keep in consideration N versus C. C is the amount of DNA notation. I apologize in advance, sort of, because the notation system you're going to see is very different than that used in the book. But I'm also going to hopefully show you that the book is almost always wrong, and they shouldn't use that notation system. And every biology book uses this notation system, and I'm trying to get it changed, okay? It's one of my goals, all right? And you're going to see quickly why it's wrong. And one book 10 years ago did the correct system, and sadly they got so many complaints from instructors who couldn't understand it that they stopped doing it. But you're going to see why it makes sense. So in 10 years when you're teaching and you get that decision, select the book that's right, okay? We're going to go over Punnett squares, very simple procedure to make predictions, and very importantly, we're going to talk about unlinked versus linked traits. Now I'm going to go back to meiosis. If I have two genes on the same chromosome and they are genetically linked, they don't assort independently anymore, right? They assort dependently. So we got to have a system that allows us to know when we look at notation whether the traits are linked or unlinked, because they give drastically different predictions. So the system we use will allow you to tell when they're linked, and furthermore to tell which specific alleles on each chromosome, okay? So again, plug your number sets chromosomes. If you want to think about this deck of cards, the suits versus card types. So the king, queen are types of cards or types of chromosomes, and the suits, ace, hearts, whatever. Chromosome structure, remember, we have that centromere position where those microtubules attach, okay? We have genes and loci. Loci is just a physical location on this chromosome. So when I talk about two genes, I can also talk about two genetic loci, two positions, okay? And mitosis, meiosis, we've gone over that. We've gone through the cycle. So let's just pick a gamete, a sperm and egg. So this is clearly haploid, this is clearly haploid. So let's just call the amount of DNA in this cell 1C and 1C. So when we make our zygote, it's 2N because we have two sets now, and there's twice as much DNA here as in either of those cells. And then when we go through the S phase, what happens to the C value? It goes from 2 to 4, and actually grows gradually, because you know about those bubbles of replication. So the number goes from 2C to 4C gradually as you go through that DNA replication, okay? But you don't change the ploidy. You've gained no new sets of chromosomes, okay? All right? So the C is a useful value. It allows us to talk about the fact is when we go through that first meiotic division, we change the ploidy. And the second division just changes the chromatid or chromosome number, okay? The amount of DNA, all right? There's a thing I was going to say about that. Anyway, if I remember it, I'll tell you. So here just shows you the chromosome. Is this duplicated or unduplicated? How many chromosomes are shown? How many chromatids? How many double-strand molecules of DNA? 1, 2, 4, 2. Here's one double-strand DNA molecule. Here's the other. Remember, you had one double strand like this. When you duplicated it, you get two double strands, but they're really stretched out, and when they condense, you see them as sister chromatid, okay? And remember, they can potentially cross over during prophase 1. So when I talk about meiosis, I have to be careful to say prophase 1, metaphase 1, anaphase 1, telophase, or just say PMAT1, and then likewise PMAT 2. Question in the back. No, they are not. This is one chromosome because they share a centromere. Okay, so the moment they separate, and those chromatids are apart from one another, this is now called a chromosome and a chromosome, because they do not share the centromere. Okay, does that make sense? I will not ask you how many chromosomes are present there, because I think it's too confusing. I will pick an end stage, like telophase 1, after you reform the nuclear membrane. Is that clear? Okay, because then I don't have to worry about, gee, you had one chromosome, you now have two, and it's the same common cytosol because we haven't formed the nuclear membrane. So I don't ask about those intermediate stages typically, okay? Because it's just too confusing and ambiguous. Any questions? Okay, let's move on. So this just shows you a karyotype here for a human. So is this, what stage of the cell cycle would this be? Would this be G1? G2? No, because G2, the chromosomes would still be extended. So in particular, this would have to probably be prophase, because the chromosomes are completely condensed, and it's, you see, chromatids, okay? And you saw this for the onion root tip. Should that have been mitosis or meiosis in the onion root tip? Mitosis, because they're making more root cells. They're not making gametes there. That would be in the flowers. And for mitosis, remember, they come in pairs, homologous pairs. In this case, there's 3. They've duplicated. They pair up during prophase 1, and then during prometaphase, they jockey to the metaphase plate, and then they separate during anaphase 1, and they separate members homologous pairs. But crossing over potentially could occur, okay? Question. C refers to the amount of DNA. Now, people will tell you it refers to the number of chromatids. That's going to confuse you, so just don't think that way, okay? All right? So C is the amount of DNA. I can artificially make whatever value I want to be C. So if I wanted to go back, and it doesn't make sense to do this, but if I wanted to say this cell here is 1C, because I artificially say that amount of DNA is 1C, then what are the gametes? Half C, okay? So typically, the thing that makes the most sense is to pick the phase of the life cycle that you have the lowest amount of DNA and say that's 1C, okay? But there are times people don't do that, okay? But that's probably the best way, right? Any other questions? All right? So back to this. Okay, meiosis, 1 duplication, 2 divisions, pairing those homologous chromosomes. First division, separate homologs, change the ploidy. Second, separate the chromatids. This just shows you the microtubules attached to that centromere. There's proteins there that they attach to, and then you pull apart those members. And crossing over may or may not have occurred, okay? This is showing you that there's a crossover there, and when we pull this apart, we'll get physical exchange. Now, crossing over is a random event. So if I have, and it only occurs on traits on the same chromosome, right? So it occurs with linked traits on the same chromosome. If the two genetic loci are really far apart, since this is a random cut, for example, you want to stand up? Pretend you have some scissors, just going to cut the DNA. She's taking off her glasses for safety. And hold your hand out like that, pretend you're scissors, and you're going to cut the DNA. Now close your eyes, spin around, and cut. Okay, that's good enough. I cut. All right, if I held this really far apart, the chance that she would cut would be greater than if I held it really close, right? So in fact, recombination is a reflection of that. We will look at the number of recombinants. If we see a large number, it meant those two loci were far apart. If we see a low number, it meant they were close together, okay? Does that make sense? And it's all relative because it's random. Thanks. Okay. Now, I have to put a little asterisk there. There are sometimes parts of the DNA that have a little bit higher recombination. They're called hot spots. There's some parts that have less. They're called cold spots. We'll ignore that. Just say it's proportional to the distance, okay? And then this just shows that crossover event. Here you can see those plasmatoforming. And this is a summary figure showing you that crossing over is literally a physical breaking of the DNA and exchange. Okay. Now, I asked you last time to draw mitosis and meiosis for 3 chromosomes, 3 pairs. Hopefully you did it, because it would make a lot more sense. Realize that when we have loci that are linked, they're along this chromosome. Here's one arm, that's the other arm. And in this case, this individual here is heterozygous for the E locus and heterozygous for the A locus. Heterozygous because this chromosome, that information, that allele is different than that. Likewise here, okay? And I show 4 chromatids because there was homologous pair with their sister chromatids that line up. So when they line up in that metaphase plate like this, there can potentially be crossing over. If the crossover event is between E and A, we generate a new chromatid that did not exist before, right? We'll have a piece of DNA that has the pink plus the blue, so it would be E, A plus. So our notation system for this, you're going to see is very useful. It would be written like this. E, A over E plus, A plus. And that does not equal EA plus over E plus A. Because in this case, these two alleles are coupled together on the same chromosome. Some people call it in phase. And the wild type alleles are coupled or in phase. It's different here. So let's think about predictions. Let's say these two loci are close together. We will get a parental chromosome and parental. That means a lot of times when we make the gametes, and we're talking about a population here. So in humans, males, I don't know, I've been lecturing for about 50-some minutes or so, 30, 45 minutes. I don't know how many sperm I've made this time, but there's been 100,000, let's say. It's true for all the males in here. It's not just me, okay? So I'm making a population. And that's key to understand. So a lot of times I get no crossover event. So those sperm would have an EA and a E plus A plus. So if I look at the genes, the alleles in that sperm, it's that and this. This is biology, come on. Notice this notation system is so powerful. I'm going to redraw this with colors to try to drive the point home even clearer. EA, E plus, A plus, E plus, A plus. So a crossover event here would look like this. I'm going to do just the two inner ones. EA, EA, E plus, A plus, E plus, A plus. So the results of this would be a parental type chromosome, a recombinant, the EA plus, the recombinant E plus A, and the parental E plus A plus. So from this recombination event, when I make my gametes, there's going to be parentals, but also recombinants. So again, we're dealing with a population. So my two recombinant forms, I'm write this little case R, would be EA plus, and the other recombinant E plus A. So hopefully you can see how this notation system is so useful. And let's say the recombinants were 10%. Let's make it 20%. Math's a little easier. 20% is the same as 0.2, which means this is 0.1 and 0.1 in terms of the population of gametes made. So if this is 20%, what's the parentals? They have to equal 100. 20%, 80%. So 0.4, 0.4. For this parent, when they make gametes, 40% will be like this, 40% like that, 10% like that, 10% like that. But realize if so this is going to say parent 1, so I can keep track. If this had been parent 2, okay, notice in that case, this would be the parental, this would be the recombinants. And if it was 20 units, this would be 0.1, 0.1, 0.4, 0.4. They're the same four types, but the frequencies vary. That's why it's critical to use this notation system, because we know exactly that these two alleles are on the same chromosome versus these two alleles versus these. Okay, I'm going to do this again. So I'm going to just write this out because I see some puzzled looks. I get a parental here, which would be EA plus, that chromosome. I get a parental here, E plus A. And my recombinant would be E plus, A plus. And my recombinant would be EA. And we had said it was 20 map units, so that would make this 20%. And this one, 80%. Okay? Whoops, I did that wrong with numbers. This should be 0.1 and 0.1, 0.4 and 0.4. Because the parentals would be the higher number, okay? All right? So we're going to use this system, this notation system, where we write one chromosome over the other. And remember, it's a reflection of meiosis. So when I talk about this homologous pair, that's going to be different than another homologous pair, right? They will assort independently. Assort independently because they're different homologous chromosomes. But if they're linked genetically, they will not assort independently. So I guarantee you on the lab exam, there'll be a question like this, and they'll say, what's probably getting offspring with this? Question. Okay, the question is, how did I decide 80%, 20%? I made those numbers up. In order to teach it, I had to make some numbers up, okay? The recombinants will always be less than the parentals. Now, in a real-life situation, how would I know how far apart the genes are? I would do an experiment. I would mate some organisms. I would look at the offsprings, and from the offspring, I could tell you how many of them got a parental chromosome, how many got recombinant, and I could do the map distance from the data. You'll do that in lab. Question. Okay, so in white, this was parent 1. Any question about that? Parental chromosome, I wrote P, EA, E plus, A plus. I wrote the letters P, recombinants were EA plus, and E plus A. I wrote the letters R to indicate recombinants. We said it was 20 map units, I put 0.1, 0.1, 0.4, 0.4, okay? I then said, I wanted to illustrate why this notation did not equal this. So now for this parent 2, we said a parental chromosome is the EA plus, so that's that, is that okay? And I said the other parental chromosome is E plus A, that's that. So then the recombinants are EA, that, the letter R, and the recombinants E plus, A plus. So I wrote the letter R, P, and P. And the map distance is still 20%, so then I wrote 0.1, 0.1, 0.4, 0.4. But notice, these give you different predictions. If it was like parent 1, you would say most of them, the largest number would be wild type, mutant. But if I'd written it this way, you would say that the wild type would be the lower number. So you might think these equal one another notation. Hey, all I did was just, mix it up a bit. They don't equal one another. This notation system allows you to tell the difference. It allows you to make exact predictions because it allows you to know which alleles are on which chromosome. Okay? Any questions? Okay, let's just quick do this. So if I asked you this question, you should be able to answer sort of this thing. What's the phenotype, et cetera. Okay, so let's quick do something like this. How many of you actually drew meiosis, mitosis last week for 3 pairs of chromosomes? So be honest, raise your hand. Okay, keep those hands up. Keep the hands up, those of you who did this. Keep your hands